Welcome, BMB510, MNE525 class. We're going to finish up what we started on Tuesday with our week of biothermodynamics. I'm going to continue by talking about ATP synthesis. Of course, as we talked about on Tuesday, ATP means energy for the cell. ATP is the equivalent of energy in the system. If your system is a human, a mammalian, a bacterial yeast cell, whatever kind of cell you want, ATP, if we are talking human cells or other mammalian cells, is made in the mitochondria. And you can see a little artist rendition of the mitochondria here. And it's kind of centered in the mitochondrial membrane, where there's an electron transport chain that uses proton gradients, electrochemical gradients, which we'll be talking about later, to foster the production of ATP from ADP, which is hydrolyzed ATP, a recharge of the ADP to ATP. So then ATP can be used to couple reactions for things like the production of glutamine or other unfavorable yet very desirable for the cell types of reactions. And so the energetics look like this, where we have the ATP hydrolysis, that high energy, as they call it, phosphate bond gets cleaved, and under physiological conditions that gives a delta G of negative 30 kilojoules per mole. So that's energy released, and that energy can be used to do work. And in this case, we're talking chemical work that is available, again, for those highly desirable reactions, but those energetically unfavorable reactions. And here is one of the prime examples of that, taking glutamate plus ammonia to make glutamine. Under physiological conditions, if we were to try to run this alone, of course we could not. The delta G for that is positive 14 kilojoules per mole. So it's very unfavorable, and then again, if we ran that on its own, we wouldn't be able to. It is impossible. So we have to couple it with something that is energetically favorable. And we can calculate the equilibrium constant for glutamine synthesis, and we get this low number here, 0.0044. And the definition of the equilibrium constant, the old-fashioned way here, is, again, we're looking at the concentrations of the products over the concentrations of reactants. So very few molecules of glutamine would be made. Again, giving props to the fact that this is a very unfavorable reaction on its own. So we need to couple it with something in order to get a little more glutamine here. The cell needs more glutamine. So it's convenient, like we just did, to define our equilibrium constant in terms of chemical concentration, especially if we're talking about dilute solutions, because if water is in the mix, then the concentration of water is essentially 1. That X equals 1, like for almost all biochemical reactions. So if we have a two-component chemical system here, if we have solute B and solvent A, the concentration of B is, the molar concentration is the number of moles of B divided by the number of moles of A plus the number of moles of B, or the total number of moles in this case. But if we've got a really dilute solution of B, then essentially that Na plus Nb is basically roughly equal to Na. So we could simply write Nb over Na as our molar concentration, and we wouldn't be wrong about that. We can put it in terms of volumetric concentration, where we have the Cb is the number of moles of B divided by the volume in liters, or whatever volume you choose to use, of A. Typically we go with liters. So again, we've got a concentration, there are a number of moles of B. We could figure that out in this way, but just by rearranging the concentration equation. Xb, the molar concentration, is just the volumetric concentration of B multiplied by the number of liters of A divided by the number of moles of A. And so with this we can update our equilibrium constant equation. In biological systems, the solvent, if A is our solvent, the theoretical A, is always water. So that Na per liter is 55.55 moles per liter. There are 55.55 moles of water per liter. And if we bring that back to the glutamine synthesis equation and the equilibrium constant for that, you can see we can rearrange the equilibrium constant in this way, where we have that 55.55 multiplied by the concentration of glutamine, the X water, divided by the concentration of glutamate multiplied by the concentration of ammonia. Note that we don't have C water here, we have X water, so the mole fraction of water is not replaced, again, because this is not a dilute solution of water necessarily, it's almost all water. So the X water basically equals 1 here in this case. So and this shouldn't actually be, this is not a dilute solution, this is a dilute solution of everything else in water. It's not dilute in terms of water, just to clarify that a little bit. So since X water equals 1, and if we can provide a physiologically reasonable concentration of ammonia, and you can find in some textbooks a list of physiologically reasonable concentrations of popular metabolites, we can get that concentration of ammonia as 0.01 molar per liter. We find that if we do a ratio of concentration of glutamine to the concentration of glutamate, we're much favoring, again, this is on its own, we're not coupling this to ATP hydrolysis yet. If we were to try this on its own, the concentration favors heavily glutamate, so the reaction essentially wouldn't really run. So on its own, it is virtually impossible to make any glutamine using the reaction as written on its own, because of that increase in free energy that's involved here. The cell would only convert 1 in a million molecules of glutamate to glutamine if it relied on this reaction on its own. So again, not necessarily impossible, but very, very, very improbable, to the point where we might as well call it impossible. So you can see with our manipulation of the equilibrium constant and the manipulation of the concentrations, that you can see the unfavorability of this reaction, this glutamate to glutamine reaction on its own. So how does the cell deal with it? Well, we already talked about that. The cell overcomes this unfavorable free energy by coupling this glutamate to glutamine reaction with ATP hydrolysis. And so the coupled reaction would look like this, where we have glutamate plus ammonia or ammonium, and the glutamine synthase would hydrolyze ATP to get the energy. The enzyme would hydrolyze ATP to ADP and phosphate to get the energy and give us glutamine. And again, I said in the beginning, hydrolysis gives us a delta G of negative 30 kilojoules per mole. Glutamine synthesis is about 14 kilojoules per mole, so the combined reaction is favorable still, with a delta G of negative 16 kilojoules per mole. Since delta G for this combined reaction is large and negative, negative 16 kilojoules per mole is large and negative, clearly it's negative, the equilibrium constant will be large, and the K for this coupled reaction is about 493.5. Much different than what we saw if we were just running this thing on its own, where our K was about 0.0044. On its own, very low, and the coupled reaction much, much higher. Orders of magnitude higher. So in cells, we ask the question, how is there ATP present to participate in these coupled reactions? I already showed you that drawing in the beginning, that image that shows how ATP is made. And ATP is made in bacterial cells in this way. It's made in the mitochondria of eukaryotic cells in this way. Equilibrium. But if we think about it in a purely thermodynamic level here, the equilibrium for ATP hydrolysis would occur when there's nearly no ATP left. Water is always going to be around. It's just how it is. We're 90% water or so. So water is going to be around to participate in the hydrolysis reaction. However, what we've discussed basically that reactions do or do not occur, or are likely to or likely not to occur. We've not discussed the speed at which reactions occur. So you may puzzle yourself over, well, how is the ATP even stable? How is it available to participate in these reactions? It's impossible for a system to move on its own free energy increase. In fact, for all intents and purposes, it will end up looking like a decrease in free energy. Living systems, our bodies included, bacterial cells, yeast cells, plant cells, whatever, are not in equilibrium. Much of what we do and what other organisms do to remain alive is to control the rate at which processes move towards equilibrium. And ATP hydrolysis is a big one of that. In living systems, ATP hydrolysis never achieves equilibrium. If it does achieve equilibrium, we might be dead or nearly dead. Alright, so let's move forward on thermodynamics here. We've talked about reactions that happen in the cell. Let's talk about some important biomacromolecules and the thermodynamics of these molecules. So we think about DNA. A long strand or several long strands of DNA are in all of our cells. Bacteria have large circular pieces of DNA in their cells. And DNA, when cells are dividing, will be denatured, copied, and renatured. So they'll at least be denatured. And we can manipulate DNA by denaturing it. And we can determine denaturation of DNA by measuring the optical absorption as temperature increases. So we can find out at what temperature DNA really denatures, whether it's one temperature or a range of temperatures. And a lot of that will depend on what kind of base pairing is in this DNA. Tightly coiled DNA in helix form, which a lot of DNA is like that, will not absorb and scatter a whole lot of light because it's very tightly coiled. The nitrogen bases that would probably absorb a lot of light, a lot of them may be obscured because of the coiling process. But as DNA denatures, or as biologists would say, as DNA melts, those loose, floppy single strands will have their nitrogen bases flopping around in the liquid, in the solvent, and those will scatter more light. And so this has been done many, many, many times, but we can look at a DNA denaturation renaturation curve. So we can first look at DNA denaturation when we take DNA from a tightly coiled mass to open floppy strands, essentially. So we look at the graph here and kind of the guide that we can go with here. We start at a low temperature. DNA remains tightly coiled, so it remains right here until its melting temperature. And it'll hit its melting temperature often. Again, the exact temperature depends on what DNA it is, like where it comes from. The melting temperature, or TM, is about 80 degrees Celsius. After that, or at the TM, the DNA will rapidly and completely denature. And then up here, you see a giant increase in absorbance because the DNA is now 100% denatured. During cooling, and what we call renaturation, the process very gradually reverses itself and looks like this. This is what renaturation looks like in sort of a way here. It is not this all of a sudden type of process where it suddenly goes back to being tightly coiled and base paired together and all that. It slowly gets there until these two curves meet, essentially. So we're seeing two different phenomena here. It's reversible in a way, but the denaturation process definitely does not mirror the renaturation process. And we can think about this in terms of equilibrium constants. So we can examine the equilibrium constants for clues about the denaturation of DNA. So, we look at the normal equilibrium constant equation. We have e to the negative delta g divided by RT. We can change that because we know, our famous Gibbs free energy equation, delta G equals delta H minus T delta S. So we can substitute delta G here for the H minus T delta S in this equilibrium constant equation. And so for denaturation of DNA, the equilibrium constant changes rapidly over a narrow range of temperature, as you saw in that denaturation curve. So that goes to say that delta S must be, and experimentally has been determined to be, quite large. The DNA molecule does not denature until a fairly high temperature is reached, 80 degrees C. And we can correctly conclude that the delta H is high also. Not surprisingly, we have a high delta S here because native DNA is a highly ordered structure. So with a high delta H and a high delta S, we can see that we can justify the rapid change in equilibrium at a certain point, at that melting temperature, Tm. So what about renaturation? Why does renaturation is longer and steadier? Besides the obvious thing that slow and steady wins the race, which has nothing to do with thermodynamics and has nothing to do really with what we're talking about here, why does it take longer than denaturation? For that, instead of quoting Aesop's fables, we can consider the forces that hold the strands together. So the arrangement is such that one base pair will not be melted at a time if we go back to denaturation. So we're not going to just melt this base pair here, then this one, etc. It's all going to happen pretty quickly. However, renaturation can do this. It could go, if we were to hypothetically renature this tetramer of DNA here, it could go this nucleotide pair, then this one, and this one, or more likely this one, or something like that. But it would go one at a time is the point. Whereas denaturation might blow these apart all of a sudden and all pretty much together, renaturation is a slower and steadier process. How do we discuss this thermodynamically is the question. During heating, again, we're going back to denaturation, the delta H and delta S are for the entire strand of DNA. And thus they're obviously going to be, since the DNA is very large, the delta H and delta S are going to be very large. During the cooling and the hopeful renaturation of DNA, what you're going to see in the phenomenon that happens is that small clumps of DNA are going to come together. But there's still going to be large sections of DNA that haven't come together and rebonded yet. So the clumps of DNA will bond together without affecting the other nucleotides. And this will just happen over time. And so basically you have to consider the delta H and the delta S during cooling for these clumps. And those are much smaller than the delta H and the delta S we consider for the entire strand of DNA during heating. So the temperature range, because of this smaller delta H, delta S, the temperature range required to change the equilibrium constant is much larger, as opposed to the smaller temperature range for unzipping or for melting the DNA. Now, what if we were to think about proteins? Well, proteins denature just like DNA. Proteins tend to be smaller than DNA, but they denature, and they can denature by heat, they can denature chemically. There are a variety of ways this can happen. We can look at these different proteins and see that two proteins behave somewhat like DNA, where they have a large and positive delta S, and they have a large and positive delta H. This one beta lactoglobin here is a bit different. It exhibits a decrease in energy and entropy when denaturing. But this is just to illustrate. This is not necessarily to prove a thermodynamic point about all proteins. This is just to illustrate that proteins can be very, very different from each other in terms of denaturation and renaturation. It depends on their makeup, and they have more choices of monomers than do DNA. So you'll get quite a range. We can calculate the enthalpy of denaturation by rearranging our equilibrium constant equation to look like this here. And then we can take the derivative of that equation with respect to 1 over T. And essentially what we get is the Van't Hoff equation. Now, how does the Van't Hoff equation help us? So we can take the Van't Hoff equation, we can plot the natural log of K versus 1 over T. And then we can measure that slope, and that will give us the negative delta H over R here, like you can see in this illustration. And we can take that enthalpy, the delta H0, which is the Van't Hoff enthalpy. So we can calculate the enthalpy of denaturation by taking the slope using the Van't Hoff equation. One way we can determine whether a protein, or any macromolecule for that matter, will denature in a single step or through complex multi-step pathway is by calorimetry. Essentially, we put it in a machine that heats it up slowly and in measured increments. Differential scanning calorimetry, or DSC, is the most common tool used. DSC can provide a direct measurement of that delta H we so crave. So what DSC is doing is it's measuring the heat absorbed by a system, that system being a protein or a polymer or something, as its temperature gets increased. During that temperature change, the amount of heat into and out of the system is measured. If phase changes or conformational changes, if we're talking DNA or protein, occur, this will be revealed by the increase or decrease in the amount of heat that's required to raise or lower the sample temperature. So you may need to add more heat or less heat depending on what direction you're going in. Here's an example of this. So this was some work that was done looking at a Staphylococcus aureus protein called FHUD2. It was being examined by differential scanning calorimetry. And it was being done using or not using this coenzyme or cofactor called ferrochrome. So initially what the authors did was look at the amount of heat needed to raise the temperature of the protein by 1 degree C. And you can see that's pretty low in both cases until we get to the melting or complete denaturation of the protein. And you can see the spike in both graphs A and B here. The spike is showing us that at the peak melting, the amount of heat that is needed to raise this protein 1 degree C can be upwards of 30 to 40 kilocalories per mole. If we're talking about what's going on here in graph A, or if we're looking in graph B, around 5 to 10 kilocalories per mole. In both cases, this is the amount of heat required to melt this protein, FHUD2. In graph A, what you can see is that the melting temperature, the Tm, is higher, and the heat added into it is more. The heat flow is much more than in B, where the melting temperature seems to be about 60 compared to 75 or so. And all we really need is about 10 kilocalorie per mole per degree C at peak melting. In graph A, the protein is complex with this cofactor ferrochrome, and in part B, the protein does not contain the ferrochrome coenzyme. So what can we conclude there? What we can conclude from these, and what the authors concluded, is that this ferrochrome stabilizes the protein FHUD2. And you can see that in the raise of the melting temperature and the raise of the amount of heat that needs to flow in order to affect melting. So after denaturation, what we can see is that once the protein is melted, the amount of heat required to raise the denatured protein 1 degree C is higher than it was before melting, that is. So you can see in both graphs that the heat flow is lower before melting than it is after. And then again, this is another indication that melting has occurred, and you can see this on a lot of DSC traces. And in truth, we're calling this differential scanning calorimetry because we're comparing one sample, the sample that has the cofactor in it, with another. And we're recording the differences, a reference sample, a sample that doesn't have the cofactor in it. So if we run DSC at constant pressure, the change in enthalpy is going to be equal to the change in heat. Since DSC is measuring the change in heat directly, it's also measuring the change in enthalpy. And the amount of heat required to raise the temperature of the sample 1 degree is what's known as the heat capacity, sometimes written as MCP here. CP is the specific heat at constant pressure, hence the P. The M is the mass, and usually this is the output of the DSC, is getting this heat capacity. We can also use the DSC to calculate entropy, the change in entropy, so we can determine delta S at the midpoint of the transition, where the K equilibrium constant would equal 1, logarithm of K would equal 0, when there are equally as many denatured and native proteins. Nothing negative about that. So you have as many denatured proteins as you do proteins that are still folded. And again, we look at our the natural log of K equation. We can conclude that delta G equals 0, and thus the delta S would be equal to the delta H, the change in enthalpy, over the temperature. Alright, let's move on into solution thermodynamics. Our cells are big bags of solution, so this is an important thing when considering cellular activity, the thermodynamics of cellular activity. All intracellular and extracellular or intercellular transport will occur in solution. It's the nature of our bodies. Certain kinds of work are important for these solutions. Electrochemical work is the big one. In a lot of cases, especially when we're shuttling ions back and forth, we need to overcome electric potential. And so that's how we move things like sodium, potassium, chloride in and out of the cell via the cell membrane. The electric potential inside the cell is more positive than that outside the cell. That's just the way, it's a biological fact there. The moving of a cation, let me rewind. If the electric potential inside the cell is more positive than that outside the cell. Actually, the biological fact is the reverse of that. Moving a cation, positively charged cation or particle or ion, out of the cell is energetically favorable because of this electric potential. So, we have more positive charge inside the cell than we do out. So the electric potential will, the moving of a cation would go down the electric potential, and that is favorable. Getting a cation in increases the electric potential, which requires work to be done. So it's basically like concentration. You're going up the gradient, so you need to do some work. And often in cells that requires the spending of some ATP currency. So for each ion transported, you can look at the change in the electrical potential, the PE, via this equation, which Z is the charge of each ion. If we're talking about sodium, sodium is +1, so Z is simply +1. F is Faraday's constant, which gives you the charge per mole of protons. In some cases, there's a temperature component there too. N is the number of moles transported, and this Greek letter psi is the electrical potential. So the potential of the cellular interior is usually defined relative to the extracellular fluid. Extracellular fluid is often considered to have an electric potential of 0. So, again, if we have a positive charged particle or ion going into from a place that's more positive charged to a place that's more negatively charged, that'll be down the gradient or down the potential, and it'll follow the electrical driving force. Same with a negative particle, will follow the driving force and go from inside the cell to outside the cell. And electric potential is not the only force to worry about here. We also need to think about osmotic pressure. We talked about osmotic pressure very early on, maybe the first class. At some point, we can look at water columns for a good example of osmotic pressure and hydrostatic pressure and how those balance out. We have, again, the water column with a semi-permeable membrane that lets water through but not solute. One side has solute, one doesn't. You're going to see water flow to area of greater concentration of ions. And this is easily how we can try to explode mammalian cells, by resuspending them in distilled water. But at a certain point, if you're looking at this U-tube here, we will have an unequal height of the water column. We will have hydrostatic pressure bearing down, which is going to equal that osmotic pressure, and then it's going to be at equilibrium. So we can calculate the hydrostatic pressure, and we can calculate the osmotic pressure, again, where C is the concentration of solute, R is our gas constant, and T is the temperature. So eventually the pressures will cancel each other out. Now if we have an open system where mass is coming and going, and for cells mass is coming and going, we can calculate the work required to move solute into a cell using that osmotic pressure. The cell that has solute entering is an open system. And we can determine the energy change that results from movement of a solute from inside to outside. There's no heat transfer for this, so Q is going to be equal to 0. However, there is theoretical expansion of the system, so that means that we will have a non-zero pressure delta volume work, PDV work. This could be visualized in blood cells or wall-less cells that are called spheroplasts, wall-less bacterial or yeast cells, to be precise. The internal energy of the system is going to change. More mass means more energy, with everything else being equal. The energy to make both actions possible must be supplied by the mass that's entering. So I can look at the energy in here. It's going to be equal to du plus p dv. The volume of the system equals the volume of the mass entering. The internal energy change, the du, is equal to the entering mass multiplied by the specific energy of the entering mass. So energy in is equal to the number of moles in multiplied by U plus PV in. So again, the pressure and the volume. Where V is the specific volume, big V equals the number of moles times little v, and N in is the amount of moles of solute entering the system. Okay, so we can analyze this in reverse. We look at the first law of thermodynamics. We look at the total equation for the change in energy, and we can arrive at the same place that we have by doing what we did on the last slide. So typical first law would look like this, where you have heat minus work multiplied by, you got mass in, the number of moles in multiplied by the enthalpy plus whatever kinetic energy or potential energy in minus whatever's going out, whether that be mass out, the number of moles out, multiplied by, again, the enthalpy, the kinetic energy, the potential energy of that going out. And so we can begin to cross things off here. And there's no heat. We already said Q equals 0. Nothing is going out. We're only looking at stuff going in, so we can get rid of all that. There's no kinetic energy we need to worry about here, or it's negligible. Same with potential energy. So we've essentially arrived. This has essentially put us here. And so how is this possible? So we consider a cell with a solute concentration of C1 in solution. And that solution is a solute concentration of 0. So this is C1 is non-zero, the solution is 0. Osmotic pressure will be acting to force water into the cell and force solute out of the cell. The network required to move solute into the cell to achieve a concentration different from C1, C2, is shown by this. And delta U is the internal energy, same as delta E on this slide here. Delta U minus the work needed to get something into the cell, a solute into the cell, multiplied by the number of moles in, or plus the number of moles in, multiplied by the internal energy here of the solute, plus the pressure and volume specific to the solute coming in. The specific U for the system will not change, so delta U basically equals N in, U in, and we can simplify this equation to the work done is equal to the number of moles in multiplied by the pressure and the specific volume. We want the net work required to perform the action of moving solute in against the gradient here. So we must set, for that we've got to separate out expansion work performed against external pressure, that hydrostatic pressure. So the net work plus the external pressure times the change in volume is equal to the, again, the number of moles in multiplied by the pressure multiplied by the specific volume. And the change in the volume of the system is equal to the volume of the entering solute. So we can rearrange our net work equation to equal our pressure in minus the external pressure multiplied by the change in overall volume, big V volume this time. Where this P in minus P ext is osmotic pressure essentially, and W net is the work available to move mass into the cell. Okay, so again, we go back to these concentrations here. We can integrate from concentration C1 to C2, whatever our initial concentration was, to the new concentration that we want, by first observing that C is roughly equal to 1 over V, and our change in volume is equal to 1 over C squared dC here. So we can integrate, and we can rewrite the equation taking into account the definition of osmotic pressure, the number of the concentration times R times temperature. And then we end up with this work needed to increase the concentration from C1 to C2 is equal to negative RT times the natural log of C2 over C1. Okay, so we've thought about two different forces here, but let's not forget about one over the other here. There are two forces that will act on charged particle as it moves through the cell membrane. We've talked about the osmotic force, but there's also the electric force. And we talked briefly about the electric potential. If membrane is permeable to cations and the concentration is greater inside the cell, cations will come out, driven both by osmotic and electric forces. Once enough cations have left the cell, the electric force pushing cations in equals to and balances the osmotic force pushing them out. Thus, equilibrium has been reached in this case. But we have an electric force in the cell to worry about too. Eventually the force balance reached and the flux stops. We look at this equation here as being an equilibrium equation of sorts. We can solve the equation for electric potential, which gives us the very popular Nernst equation. And this is for membrane equilibrium. So the change in potential is equal to negative RT divided by ZF, and again Z is the charge of the ion, F is the Faraday's constant, multiplied by the natural log of the concentration in divided by the concentration out. Okay, so that's all I'm going to say about that. There's an assignment posted on my courses, should be available today. There are 10 questions related to thermodynamics and biological systems. That assignment will be due on Tuesday, October 3rd. It's not due on this coming Thursday because I will not be around this coming Thursday. It'll be due at the end of class on October 3rd. And since these are mostly math problems, you will probably want to, whatever's easier for you, you'll probably want to just write them out by hand in a legible format and hand them in to me as class ends. One thing to note, there's something you haven't seen before, something I haven't talked about today until just now in this assignment. You're going to look at thermodynamics of DNA denaturation. So you're going to look at the delta H and delta G and the entropy of small DNA strands. So you'll see this table is part of it, and there's an equation that goes with this table that basically gives kind of this unified theory on calculating the thermodynamic constants of, or the thermodynamic properties, I should say, not constants, of DNA based on the types of base pairs that are available. So if you're given a certain segment of DNA and you want to know the thermodynamic properties, you can basically you're additive to this table here. Or if I have an ATTA base pair where A is hydrogen bonded to T, T is hydrogen bonded to A, this will be the delta H, delta S, delta G at 37 degrees respectively. And then you'll notice that not all permutations are available. And this will affect one of the answers. If you don't see the actual permutation available for you, use the closest one that's available. So you'll notice there's CAGT, but there's no ACTG, right? So if you're looking for ACTG, just use CAGT here as your thermodynamic properties when you're being additive about this. And there's more in the more detail in the homework itself. If you have questions, should be available by email. Okay, that's that. And good luck with the assignment. And let me know if you have questions or concerns on that front. And I will see you not next week. We will have another online class, probably recorded lecture next week as well, plus an online assignment then. So I will see you in October.